We're moving on to section 5.8, and we're going to talk about the average value of a function. Now, in second semester calculus, Math 5B, we will be starting by going over a bunch of applications of the Riemann sums. We started out the Riemann sums using them to find the area under the curve, and here's what we went over. That when we have a Riemann sum that looks like this, we can rewrite it as a definite integral, and we can find the value of this infinite sum by using the fundamental theorem of calculus, right? And so if we come across a situation where we can write it as a Riemann sum, and then we can change it into a definite integral, and then use the fundamental theorem of calculus to do that. So that's what we're doing. We're only going to look at one example of this application, and it's going to be in the finding the average value of a function over an interval. So let's just briefly review what the average is, right? So you receive scores of 87, 93, 78, and 90. What was your average score, right? And so you guys know how to do this. To calculate your average score, you add up all your scores, your 87 plus your 93 plus your 78 plus your 90, and you divide it by the number of scores. There are 4 scores, and so then that is your average. So 87 plus 93 plus 78 plus 90 divided by 4 is your average score is 87%. You've heard things like this, the average temperature for a day. How would you define the average temperature for a day? So the difference between what we were doing before and what we're doing now is that before we had a finite number of scores. In the last example, we only had 4, but we could have a lot more than 4. And so if we only have 4 scores, we add up the scores and divide by the number of scores. So how would you do that for a day? Well, you could take a temperature reading for every hour, and then add up those temperature readings and divide by 24, the number of hours. If you wanted to do a better job, you might take a temperature reading every minute and then divide by the number of minutes. If you wanted to do even better, you could take a temperature reading every second, right? And what you're seeing there is kind of like, should be reminiscent of when we were trying to find the area under a curve. We just make our interval smaller and smaller and minimize the area. Minimize the error. Okay, so let's go over then that same idea on how to apply that to the average value of a function. Let f be a continuous function over the interval from a to b. First, we could divide the interval into n equal subpieces of with delta x equals b minus a all divided by n. In each of those intervals, choose an x sub I to evaluate your function at. And now this is how you would get your approximation. You would add up all those output values and divide by the number of output values. And when you look at this, what you should recognize is this does not look like a Riemann sum. And the reason why it does not look like a Riemann sum is because you don't have a delta x, right? So the Riemann sums had a delta x. This does not. But what we could do is we could substitute in for n using this formula right here. So this formula, we could solve it for n and write that n is equal to b minus a divided by delta x. And so then if we go and replace the n with b minus a divided by delta x, then multiplying the numerator and denominator of this fraction by delta x, the delta x's will go away. And what you will get is 1 over b minus a out in front, because we could put that out in front, and then times, let me see if I, so what we will get is 1 over b minus a out in front, and then you have, we can factor that out, and then you will have f of x1 star times delta x plus f of x2 star times delta x plus f of x3 star times delta x plus dot dot dot, and then f of x, and then that then becomes your Riemann sum. So then if we take the limit as n goes off to infinity of the summation of this 1 over b minus a can come outside, and then this is the summation of f of x sub I star times delta x, and this looks just like a Riemann sum, and so then this becomes 1 over b minus a times the definite integral from a to b, and then f of x dx. And so using, or from here, then we can make this definition that if f is continuous on the interval ab, then the average value or mean value of f on ab is defined to be 1 over the width of the interval, b minus a, times the definite integral from a to b of f of x dx. And so now we can find averages not just of discrete expressions, but of continuous expressions as well. Not just when you have a finite number of points, but when you have an infinite number of points where you have a continuous function that connects all those points. So find the average value of the function over the given interval. All right, so this is then just 1 over b minus a, 8 minus negative 1, times the definite integral from negative 1 to 8 of the function, which is we should rewrite as x to the 1/3 dx. So this is 1/9 times the antiderivative is add 1 to the exponent, 4/3, multiplied by the reciprocal 3/4, evaluated from negative 1 to 8. 8 to the 4/3, so they both have a 3/4, so let me go ahead and bring that 3/4 out, and then we will have 1/12. And then we have 8 to the 4/3, and what 8 to the 4/3 means is it means to take the cube root of 8 and raise it to the 4th power. Minus negative 1 to the 4/3, which means the cube root of negative 1 raised to the 4th power. Don't panic because you have a negative under the radical. It's an odd radical, so that's perfectly okay. The cube root of 8 is 2, raised to the 4th power is 16. The cube root of negative 1 is negative 1, raised to the 4th power. Since it's an even power, it will be a positive 1. And so you will get 15/12. The average value of this function is exactly 15/12. Let's move on. Find the average value of the function over the given interval. So you have the function secant x tangent x. And so then again, it is 1 over the pi over 3 minus 0 times the integral 1 over the width of the interval. times the integral from 0 to pi over 3 of the function, which in this case is the secant of x, tangent of x, dx. You should recognize this integral as being something that is on your table. And the antiderivative of the secant tangent is the secant. And for this 1 over pi over 3, we can multiply the top and bottom by 3, and we will get 3 over pi. And then the antiderivative of the secant tangent is the secant. And we're going to evaluate it from 0 to pi over 3. Pi over 3 is 60 degrees, 30, 60, 90 triangle. This is 60 degrees, this is 30 degrees, this is 1, this is 2, this is the square root of 3. The secant is the reciprocal of the cosine. The cosine is 1 over 2. The cosine of 60 degrees is 1 over 2. So the secant of 60 degrees is 2. So you get 3 over pi times 2 minus, and when you put in 0, the cosine of 0 is 1, and so the secant of 0 is also 1 because the reciprocal is also 1. And so then 2 minus 1 is 1, and so you just get 3 over pi. That is the exact average value of this function over the interval from 0 to pi over 3. Suppose that the acceleration function of a particle moving along a coordinate line is a of t equals t plus 1. Find the average acceleration of the particle over the time interval from 0 to 5 by integrating. Okay, so you know your acceleration function. To find the average value of a function, you integrate. So then it is, for part A, it is the definite integral, 1 over the width of the interval, which is 5, times t plus 1, definite integral of the average of the function, t plus 1 dt, and then we're going from 0 to 5, which is then 1/5 times t squared over 2 plus t, evaluated from 0 to 5. So then you get 1/5. When you put in 0, you get 0, and when you put in 5, you get 25 over 2 plus 5. So 25 over 2 plus 5 divided by 5, math 1, 7/2. Okay, now let's look at B. Now suppose that the velocity function of a particle moving along a coordinate line is v of t equals cosine of t. Find the average acceleration of the particle over the time interval from 0 to pi over 4 algebraically. Okay, so again, you need to be careful. You were given a function, but it was not the acceleration function. And suppose that the velocity function of a particle moving along a coordinate line is v of t equals the cosine of t. Right, and so if you look at what the definition of the average value of a function is that it is the width of the interval, so which would be 1 over pi over 4, times the antiderivative of the function evaluated at the endpoints, right? And so since here you were already given the antiderivative of the function. The antiderivative of the function is the cosine of t. the antiderivative of the acceleration is the velocity, and you were given that, so there's no need to use the acceleration at all, and you evaluate it at the endpoints from 0 to pi over 4. And so then the 1 over pi over 4 is just 4 over pi. That is the reciprocal, 4 over pi. And the cosine of pi over 4 is the square root of 2 over 2. And the cosine of 0 is 1. Okay. And so there you go. That was just a matter of reading the problem correctly. Short section. So this is the section 5.8. Your homework is due next Thursday. And stay safe. Hope all is well.